I hope you're doing great and you are not too much sleepy right now. Myself, Axel Zika, and my colleagues Bernard and Iso Narcos, we will present you an interesting instrument of hackers, and it is the EMSI catcher. So our presentation will be divided in several ways. The first one will be a short story introduction, and it will be presented by myself. After, we will ask ourselves what is an MSI capture and how does it work, and Lazar will answer that question. Attacks using the MSI capture and the solution for our protection against this instrument will be answered by Joker. So, to begin with, a short story. So, we are about the 30th December 2022, so last year, one day before the New Year Eve, and a police car is doing rounds in the 10th district of Paris. So, as common, the police officer arrests the car, and they discover a 20-year-old woman that has consumed drugs. It is something that is common for them. So, as there is drugs involved, they need to do a check of the car. It's a common procedure. And this is what they found. So the first picture shows a strange routers, white routers, in the back seats of the car that seems to be attached to something in the truck. So the two policemen needs to check what it is and open the truck and see that strange black box. Then they open this box, take picture and thoughts, because there are no training in information security, that it was a bomb. So they close the nearby metro station and secure the zone and blow it up. Fortunately, as they have taken a picture, but this is the picture that they took, we can see a strange instrument in the back of the car. They didn't know exactly what it was and asked on Twitter, the user of Twitter, 4L, sorry. The Twitter user find that it was an ESMI patcher, and now we will try to understand what it was doing in this car and how does it work.
Okay, so first of all, what is an MSC catcher? So it's a type of CSS. A CSS is a cell-site simulator. So basically, it will trick the phone into thinking it's talking to a cell phone tower. So it was first developed for military uses, but now it's an advanced surveillance tool, but it's more widespread now. So for example, these two are like basic image catcher without any tenors. So MSC catcher, as the name suggests, catch IMSCA. So it's international mobile secure identity. So it's a number that is linked to your SIM card. But IMCA catcher can also catch other things like IMEA. So it's the ID of your phone. For example, in iPhone you can search it. It's there. You cannot change it, so it should be kept private because you can identify your phone. So on the edges, they can also get more information. So how does it work? So in basic communication, the GSM, for example, your phone always connects to the strongest signal. So the IMSC catcher only has to be like closer to the phone and send a stronger signal. So then the phone will connect to it naturally. It won't be suspected. Also, the IMSCA catcher doesn't need to interact a lot with the phone. Only need to take the MCA in the most basic cases. So then the phone will start talking to the IMCA catcher thinking it's a tower, and like to prove your phone, to prove that you have paid for your network bill, he has to give you your IMCA to the network. So you will give it to the IMCA catcher. So the phone won't detect anything. It won't be suspected that the phone is talking to an adversary. And once the MCA catcher has MCA, you can also get the MEA to have more information and like to track the phone, to have its location by trilateration. But we are lucky because 4J and LTE network are more secure, because in this network, your phone won't just connect to the strongest network that is close by. So, but MCA catcher are also evolving. So it's a cat and mouse game of technological evolution. So for example, there is an attack that is named service downgrading. So because the MCA catcher wants to use GSM and not 4J and LTE, he will ask to use this to ask GSM. And most of the time, the phone will accept because that's how network towers work. So, but you can also send a lot of white noises to the 4J. So 4J will become unavailable and you will use GSM. Once the EMCA catcher has the IMCA, you can also get more information. You can have communication interception. So for this, we use spoofing authentication. So how does it work? So the catcher will ask for location update. The tower will ask the MCA. So the MCA catcher already have it. Then the tower can ask a cryptographic question that needs unique ID of the SIM card. And the MCA catcher just has to give this question to the phone, take the answer, and then give it back to the tower. And then the communication will be intercepted. So MCA catcher can get a lot of information.
So I will just do a bit of storytelling, because with an MCA catcher, they can get all the phone numbers of an area, so they can have a huge data set of phone numbers and then sell them to some scammers network. I was the victim of one of these scams because they can send some messages to a lot of people, and the fun fact is that I lost my health insurance card, and 2 days after I had the message and I clicked on the link, but fortunately I blocked my card just a few minutes after, so there is nothing wrong. I will talk about the detection methods and some detection applications. So how can we detect CSS and how can we be protected from it? So for the detection methods, we first need to know that we don't really know how CSS works. It's all based on some research and how we think it might work, but the manufacturers can do a lot of things, so it's pretty hard to detect. We have some common steps, so we can see, like Lazar said, that the CSS uses high broadcast power. So maybe if we detect a high broadcast power, this means it's the fingerprint of CSS. So that's a way we can detect. And we also have like the missing normal base station capabilities, because it's not a true antenna. We don't have all the informations. The manufacturers cannot copy all the informations of the network. And we also have the ephemerality. It's only here for a short period of time. A true antenna is here always at the same place, and the EMSE is only here for like maybe 5 minutes. and this is how we can detect it. But we need to not be confused with some like testing equipment that can be here just for a few hours. So this is the hard part. So we have some detection apps that use the principles that I just explained. So we have the Android MSC Catcher Detector, Snoop Snitch, GSM Spy Finder. So yeah, it uses the broadcast power, the light change. It's when you connect to an antenna, your phone needs to send a code to ensure that you can connect to the antenna. And yeah, so for the broadcast power, some researchers analyzed the different applications, and the applications could not detect the broadcast power change. So that means it's actually not worth it to have this type of application. And for the like changes, the main goal was to compare the code between some antennas in a zone, and if the code is way different, that means it's not a true antenna. But to do it, it was pretty hard because yeah, maybe some antennas don't have the same code in our area, and so the solution was to store all of the codes that the phone have seen. But again, if you travel, you will see new antennas, so it sends false positive message, and this is a problem. There are no global standards for the cell phone communications, so this is why we cannot find a true solution to detect an MSI catcher. So this is the Android app, sorry. So we can see here we have different windows. I will talk about this map because we can see on the map that we have different antennas, and here you can see that if the antenna is red, that you don't want to connect to it, and it can slightly help you to know where you're going and to know if you need to turn off your cell phone. Because the defense method, there is no feasible way to defend, because the CSS have a huge range of capabilities. I mean, the manufacturers can do a lot of things, we don't know how it works, and so the only true solution is to turn off your cell phone.
Yeah, and here's a quick recap about what we said earlier. We did this presentation based on a video from a French YouTuber that is specialized in cybersecurity. It's very interesting. And a paper. This is our references. And yeah, thank you for listening to us, and I hope you learned something.
Questions? I have one question. So, is that possible to keep all the antennas antenna from the company, like the optical company, and give them some kind of authority? Like every time your cell phone is coming to a new antenna, just do authority.
Yeah, if it sends like all the information, because the antenna has to know who you are and if you can connect to it, and there is no way to like stop this.
So you mean when I ask for ask for some kind of authority, some kind of this already has this information and they can take it.
Yeah, because like the MSI code is owned by all the cell phone companies, so maybe they have a huge database with all the information, and that's maybe a check. Yeah.
And you need to check with everyone. Like if you want to connect in another country, it will be another way to connect. Yeah, it's another issue.
Thank you.
I mean, 5G, right? It's not implemented
No, there is implemented, but not like for
Yeah.
everyone.
Yeah.
But yeah, it's we don't have any information about that kind of that's a new thing.
But the downgrading is still possible.
Yeah, but I saw an article saying that even with 5G we are not protected. So yeah, it's a bit of a trick.
Hello, we are Group 1, and our topic is secure aggregation. And before we start it, we need to know something about what is federated learning. And we will introduce relationship between federated learning and secure aggregation. So, what is federated learning? Federated learning is a machine learning approach. It can base on multiple decentralized edge devices. And in many scenarios, especially with sensitive data, privacy is a huge concern. Federated learning allows the training of model directly on user device without the need of sharing raw data, which can deal with the privacy issue associated with centralized data storage. And let's make a scenario. When we use our smartphone keyboard to type words, there's a useful function which predicts the most possible word we want to type. And there is actually a model behind this function. The model needs to use our typing words as the training data to make its prediction more accurate. However, text message frequently contains sensitive data, such as health records or normal behavior on your cell phone. Users may be reluctant to upload their copy to the model server, so we consider training such a model in a federated learning setting, wherein each user maintains a private database of her text message on her own mobile device, and share a global model is trained under the coordination of a central server. All the server needs to do is just update their model parameter to the central model. Because the user needs to update their model parameter, we must find a safe way to securely update them. So here comes the secure aggregation. Secure aggregation is specially designed for our smartphone. And when parameters aggregate across several edge devices, we don't want the bad guy to infer our information from the parameter we just updated. Then we need secure aggregation to ensure encryption and protection. And it also can prevent some novel attacks such as man-in-the-middle attack or data leaks attack. And next slide will let my
therefore, secure aggregation protocol need to be highly communication efficient and be robust to users dropping out and provides the strongest possible security. And now I'm going to introduce the cryptographic primitives of secure aggregation. The first is the secret sharing. This technology involves splitting a secret S into n shares and setting a threshold value T. The original secret S can only be reconstructed if one has obtained equal to or more than T shares. It is designed to address the issue of disconnections. Even if some users go offline, it is still possible to re-aggregate parameter values and share private keys when the number of available shares exceeds the threshold. The next is the key agreement. This discusses methods of key exchange, which involves how encryption keys for transmitting information among participants are exchanged, which is actually the use of Zippo-Hellman key agreement method. And the next is authenticated encryption and pseudo-random generator. And the last is the public key infrastructure. To prevent the server from simulating an arbitrary number of clients in the active adversary model, we require the support of a public key infrastructure that allows clients to register identities and sign messages using their identities. There are 4 challenges in secure aggregation. Challenges in computation and efficiency. Secure aggregation algorithms typically entail substantial computation and cryptographic operations, leading to potential inefficiencies, particularly in scenarios involving large-scale data sets. The complexity of computations might result in prolonged aggregation processes, limiting practicality. And the next is the security challenges. Safeguarding data privacy and ensuring system security is crucial during the data aggregation process. However, this secure aggregation algorithm might be susceptible to threats such as intruder attacks, information leaks, or system vulnerabilities, necessitating robust security mechanisms to mitigate these risks. The next is the standardization and scalability challenges. Currently, the absence of standardized secure aggregation protocols makes it challenging to deploy and scale these technologies across different platforms and application domains. Hence, there is a need to establish more universal and scalable protocols for broader adoption in various fields. The last is the trade-off between performance and privacy. Balancing performance and model accuracy while protecting individual privacy can be challenging. At times, to enhance performance or model accuracy, there might be a need to compromise a certain degree of privacy protection. This trade-off could pose a challenge. And next, we are going to introduce the algorithm and process of the secure aggregation in federated learning.
Okay, in federated learning, clients like a smartphone, A, B, C, have their own AI model. This model is training on their private data, so they don't want the cloud server directly get their original model. So they add their original model with 2 masks, and this mask is just lots of command number. So they get a protected AI model. And these two masks, the mask 2 is a special mask. All of the mask 2 add together will equal to 0. So when they upload the protected AI model to server just add these 3 models together and the server just the mask 1, A, B, C. Then the server can get the sum of the original model, but the server cannot know what is the original model separately. Okay, to complete this process, we need 4 steps. Step 0, 1, 2, 3. Okay, step 0 is advertise keys, means every smartphone will publish their keys to the other smartphone. So first, every smartphone will generate 2 development keys. You know, the development keys have 2 keys. One is the public key, the PK, this PK. The other is the secret key, SK. So they have 2 development keys. One is C. C means communication. This key is used for the communication between it is rather S means seed. These keys will used to be generated one kind of mask. Is that kind they will add together and they will equal to 0. This kind of mask. And the smartphone will send their public key to the server, and the server will send distributed these keys back to smartphone, but they will get the other smartphone's public key. So now we can see that the smartphone A gets the public key of B and C, and B get the public key of A and C, and C get the public key of A and B. Okay, we go to step 1. In step 1, we need a technique called the Shamir secret sharing. This Shamir is ISS-AD Shamir. This technique can split one key, is just a number, into n key fragment. Key fragment also some kind of number. And if you get T of the key fragment, you can repair the original key. This is what is the technique. Okay, you use this technique. In the thread zeros, we get those public key and secret key, and we now generate another key called B. It is another seed for the mask. It is a simple one mask seed. And we generated the key fragment of B and the S secret key. You can see this BAB means this is BS key fragment, but this key fragment will send to smartphone B, so it's called B. So when they send the key fragment to server, they will use the communication development key to encrypt it, because they don't want the server know what the key fragment is, or otherwise the server will easily repair the original key, so the server will know what the secret is. Okay, so server cannot know what the secret is and send to other smartphone. The smartphone can use their communication development key to decrypt it and get the original value, so they can safely get the key fragment. Okay, now we will next to step 2. The step 2, we will need to protect our model with the 2 kinds of mask. Okay, we can see this X is the original model and the Y is the protected model. So we will add 2 kinds of mask. One kind is use the C, the B, this B to generate. And the other kind is use the secret key, development key S as a seed to generate. And this kind of key will, because you can see this, when U greater than B, the delta will be 1, and when b greater than u, the delta will be -1. So they add together, they will equal to 0. So we use this formula to get the protected model. This pseudo-random, this PRG means pseudo-random generator because our B and this S is just one number, but the AI model has many numbers. So we need the pseudo-random generator. He takes one number as the input and he can generate many numbers. So we can protect the whole AI model. Okay, so we have this kind of stuff, and we get the original AI model and two seed, and by combine together to get a predicted AI model and then send to the server. Okay, so I will next to final step 3. We need to let the server add them together and create some kind of mask to get a truly original number sum. Okay, so we have 2 scenarios in this step. One scenario is like this: all of the smartphones successfully upload their model to the server, and because all of them are successfully upload the model, so every smartphone will send their B key fragment to the server, and the server will get this the B key fragment. It can repair the original seed B and use this seed B to subtract the mask that was generated by this seed B, and they can get some of the original model. But sometimes C lost their connection to the server because our smartphone very easy to run out of power or go out of the Wi-Fi range. This is a common thing. In this scenario, only protect model of A and B upload to the server. In this scenario, the smartphone A and B, they will not upload the B key fragment of the smartphone C. They will upload the secret key S of the C, the key fragment to a server. So now the server can repair 2 B seed and 1 secret key of the C. And in our strategy, we can see where server can easily get every key's public key. So server can use this secret key to generate the spatial mask of the smartphone C. We just use this key to generate use this formula to generate the mask need to be removed. But this is related to the smartphone C. But the smartphone C is now not uploaded model. So if in the first scenario we can just add them together to remove the spatial mask. But in this scenario, the smartphone C not uploaded its model, so we need to remove its spatial mask in this way. Also, in this segregation, we can prevent smartphones' private data from being leaked out from their original AI model. And if some of the smartphones are lost their connection, we can also reconstruct, also successfully FGate when their number are still up, still greater than we set the n, the T out of n key sharing. So this is our presentation. Thank you very much. Any questions? Or you want to know how the key sharing is achieved? I can write a formula. Lagrange polynomial. You just want to go home.